Okay, I want to look at the gamma function and just kind of introduce you to it. The gamma function, of course, this is when you see this little symbol here, this Greek uppercase gamma. This is how we usually indicate that we're working with the gamma function. Now, the gamma function is an improper integral, as you can see here. It goes from 0 to infinity. And notice this, that the gamma function has the independent variable is t. However, the integral we're evaluating with respect to x. Now let's see how we would evaluate the gamma function for some positive integer, or just really anything. We're just going to plug in for t. Let's say gamma of 6. Well, notice that what I do is in place of t I put the 6, and then we have this integral, which of course is an improper integral, and the way that we deal with that is to rewrite it as a limit. Now, the problem that we face is, well, how do we find an antiderivative for this integrand? Well, obviously, the method that we would take would be integration by parts or tabular integration, which is a shortcut. So that's what I'm going to do. I'm going to take the x to the fifth and just start differentiating it. I keep repeatedly differentiating x to the fifth, first derivative, second derivative, third derivative, fourth derivative, fifth derivative, and I keep going until I get 0. Then I take the other part, the e to the negative x, and I find the antiderivative of that. So the antiderivative of e to the negative x is negative e to the negative x. The antiderivative of that, e to the negative x, and so forth. And I keep going until I'm lined up with the 0. Then I draw my diagonals and alternate signs. Now here's what's going to happen. I'm ready at this point to go ahead and write out an antiderivative for this integral. So here it goes. Now notice that every term in this antiderivative is negative. And let's notice how that happens. First of all, this first term. We've got x to the fifth times negative e to the negative x. Well, of course, that's negative. There you see it. Now, the next term, we've got 5x to the fourth times e to the negative x, but we multiply by negative 1, so there we have the negative there. Now, notice that in every case, we end up having a negative term. If you look down at each one of these terms, you're going to get negative for each one. So that's why we have this. Now, let's go ahead and go to the next step and go ahead and plug in and evaluate. First of all, I plug in the b. Now, I plugged in the b, and notice that we have e to the negative x. So, in other words, we have e to the negative b. I just wrote that with the e to the b in the bottom, and the denominator made it positive. Then I subtract off, plugging in the 0 for x. Now notice that every term is 0. First of all, when we evaluate this limit up here, the e to the b's in the denominator mean the denominator just blows up much faster than the top. So every one of those terms goes to 0. In the second one, down here when we plug in a 0 for x, every term is going to be 0 except for the very last term. Now notice we have a negative here and a negative here. If we put those together, we're going to get a positive. 5 times 4 times 3 times 2 times 1, and of course that's 5 factorial. Now you could continue on with this, and what you would note is that whatever k you put in there, whatever number you put in, whatever positive integer, gamma of k is going to be k minus 1 quantity factorial, provided that k is a positive integer. Now, let's see what would happen if we put in a 1/2. Well, what we get is then we get x to the negative 1/2 e to the negative x. So now our task is to evaluate that. So here's what we want to do. I'm going to make a substitution. I'm going to let x be 1/2 rho squared. Now if I do that, dx is rho d rho. Now I plug that in. Just plugging in, and here's what we get. We get this integral simplifies to the integral from 0 to infinity square root of 2 e to the negative 1/2 rho squared d rho. Now, we have to figure out how to find that value. We have to figure out what that is. So here's what I want to do. I want to harken back to the normal probability distribution, this integral here. And notice that this integral goes from negative infinity to infinity. It has these parameters, sigma and mu. And what we know about this integral is this integral, if you go from negative infinity to infinity, the value is 1. Definitely. We know that to be true. And we also know that this integral is symmetric about mu. So half of the area under the curve is to the left of mu, and the other half is to the right. And what we get is a bell-shaped curve, like this. Now, what I want to do is look at a particular case of this distribution where mu is equal to 0 and sigma is equal to 1. Now, when we do that, what we have is the standard normal distribution. And this particular graph would be symmetric about 0. Okay, now let's see what our integral looks like. Here's what we have. Now, because of the symmetry, I'm going to change this integral. I'm going to, and notice first of all what I've done here is I've rationalized. I have 1 over the square root of 2. I'm just going to write that as the square root of 2 over 2. That's just me rationalizing the denominator. But now look at this. Since it's symmetric about 0, I'm going to, instead of integrating from negative infinity to infinity, I'm just going to integrate from 0 to infinity and double it. And that's still 1. So I'm integrating half of it and doubling it. That's fine. And notice the 2's will cancel. And now I have this. Now, you notice that this integral here looks a lot like our gamma function integral, except it's got a pi in the denominator. So let me factor out the pi. And look, these two are the same. So it looks like I have a way now of determining the value of this gamma integral, gamma of 1/2. Except I've got 1 over square root of pi out front. Well, if I just multiply by the square root of pi on both sides, I have this. Now this is fascinating because what we're saying is, we're saying that gamma of 1/2 is equal to the square root of pi. And I don't care who you are, you got to admit, that's kind of cool.